In this next example, we have an exponential function where the base is between 0 and 1. We have f of x is equal to 1/3 raised to the x power. We discussed earlier that this graph will be decreasing from left to right. Let's create a table of values as we did previously to get some guiding points. So again, in this case, the base a is between 0 and 1. When x is 0, y is equal to 1/3 to the 0 power, which is 1. When x is 1, y is equal to 1/3 to the first power, which is 1/3. When x is 2, y is equal to 1/3 squared, which is 1/9. When x is 3, we get 1/3 raised to the third power, which is 1/27. We're getting very, very small now for y. Let's go to negative x values. When x is -1, we get y equals 1/3 to the -1 power, which becomes 3. When x is -2, we get 1/3 to the -2 power, which is 9. And when x is -3, we get 1/3 to the -3 power, which is 27. That's going to fall off our graph. So let's go ahead and plot these points. We have 0, 1, 1, 1/3, 2, 1/9, 3, 1/27. So we see that as we move to the right, this graph will get closer and closer to the x-axis, but will never actually reach the x-axis. Then we have -1, 3. We have -2, 9. And then we're off the graph. So the basic shape of this graph will look something like this. And as we move to the right, we'll get closer and closer to the x-axis, but we'll never actually touch the x-axis. So I'm going to go ahead and add the x-axis, the line y equals 0, as a horizontal asymptote for guidance. The domain of this function is still all real numbers, so there's no restrictions on x. And the range is all positive values, so we'll go from 0 to infinity with 0 not included. So this is the parent function for this exponential decay function. In the next example, we will do a transformation to this parent function. In fact, I see two actions that must be taken. I see a horizontal translation as well as a vertical translation. This time we don't have any reflections. So for the parent graph that we just took care of, I see here that we would have to move 1 unit to the right and then 2 units up. So we could do that probably in one step. Let's start with the point that would have been at 0, 1. If I move that 1 unit to the right and then 2 units up, it lands me right here at 1, 3. The next point that I have for guidance is the point that started out at -1, 3. -1, 3. So if I go 1 to the right and then 2 up, it puts me right up here. Let's go to the point that started out at -2, 9. -2, 9. So if I go 1 up and then 2 to the right, it lands me right there. All right, let's take a look at, oops, that doesn't look right. Let me go back and erase that one. It doesn't look right. So I started out at -2, 9. And where does that land me for real? -2, 9. So we go 1 to the right and 2 up. Oh, should be all the way up here. That looks a little better because before I had 2 points as y-intercepts, and that would have been incorrect. Now to get the rest of this graph, I'm going to think about that original horizontal asymptote, which was at the x-axis. It's going to have to move up 2 units. So it's actually going to be at the y = 2 line. And anytime you're dealing with exponential functions or logarithmic functions, which we'll discuss later on in this module, those asymptotes are going to be really helpful in getting the correct shape of the graph. So I can go through my guiding points, and I know that the graph is going to approach the horizontal asymptote, but it will never touch or cross over it. So in general, my graph would look something like this. The domain is still the set of all real numbers, so I have no restrictions on x. But I do see that the range has now shifted. Now we're going to go from 2 to infinity for y, with 2 not included. Next, let's introduce a special type of exponential function where the base is a very special number called the Euler Constant. It's also called the natural number. Now, this number is named after Leonhard Euler. I know it's spelled Euler, but it's pronounced Euler. And this number, again, also referred to as the natural number, is irrational, kind of like the number pi, where if we were to write it as a decimal, it would not end nor repeat. Therefore, its exact value is represented by a symbol, in this case, the lowercase letter e, but it is irrational, so it has a non-terminating, non-repeating decimal approximation. All right, so because e is positive, and here's its approximate value, about 2.71828, et cetera, so about 2.7. So a little bit less than 3. Because it is a positive base, when we write the exponential function f of x equal e to the x power, because the base is greater than 1, right? The base is about 2.7. It's going to have that increasing shape, that J-shaped graph. On the other hand, if we write a second function, g of x equals e to the negative x power, multiplying by -1 for x is going to create a horizontal reflection across the y-axis. And so we get the graph that is decreasing from left to right. And again, if this doesn't quite make sense, write g of x as 1 over e to the x power. Or you could also think of it as 1 over e as your base. E, not 6. 1 over e as your base, all raised to the x power. Well, now 1 over e is approximately 1 over 2.7, which is a number between 0 and 1. So in the following two examples, we're going to create some transformations of the parent function that we saw just above. In example 1, we have f of x is equal to e to the x plus 2 power. So that is going to create a horizontal translation 2 units to the left this time. So notice that we have the 0, 1 y-intercept as we always do with these parent exponential functions. I always start that as my first point to plot. So if we're moving that point 2 units to the left, then it's actually going to end up right over here. Next, we had the point 1, e, which is approximately 1, 2.7. You see that point right there in the original graph? So 1, 2.7-ish is going to move 2 units to the left, so it's going to be right around here. Now, if we want a more precise graph, we can choose some additional points. So let's say that x is 0, then y is going to equal e to the 0 plus 2 power, or e squared. And let's see approximately what that would be. So I'm just going to do 2.7 times 2.7. So that's about 7.3. That's close enough for what we're doing here by hand. So about 7.3 would put us right about here. And Because this is a graph that hasn't shifted up or down, then we expect that horizontal asymptote at the x-axis to still be in place. It hasn't moved. So to get the rest of the graph, I really don't have to bother finding too many exact ordered pairs because I know the graph is going to approximate or get closer and closer to that x-axis. Now, the domain of this function is still the set of all real numbers, and the range goes from 0 to infinity, with 0 not included. Now, the next example will require us to use steps that have to be broken down, because the first thing I notice is that there is a negative x here in the exponent, which means we're back to this second example over here where we have a decreasing graph. Additionally, we see that there is a vertical translation 4 units down. So let's look at the original graph, and I'm going to erase a couple of things here just to make it a little bit less cluttered. So now we're looking at the second graph that's decreasing. We still had 0, 1 as the y-intercept. So we're going to shift that 4 units down, which will put us right here at 0, -3. Now this point right here was -1, comma, and then that's about 2.71, right? So if that point is going to move 4 units down, I'm just going to kind of start here at -1, comma, about 3.7. That's where it started. I'm going to go down 1, 2, 3, 4 units down. So it's going to land me right about there. Let me erase how I got there. Next, we have this point right there, which started out at 1, 1 over e, which is approximately 1, 1 divided by about 2.7. That's about 0.4-ish, approximately. So if I started out at 1, 0.4, about halfway there, I go 1, 2, 3, 4 units down, and so I'd be right about there. So I think this is enough to get the shape of the graph, but what I want to do now is think about where that horizontal asymptote is going to be. So that horizontal asymptote started out at the x-axis at the line y equals 0, and we're shifting it 4 units down. So the new horizontal asymptote will be right here at y equals -4. Again, super important that you think about these asymptotes as you try to complete your graphs. So I know that this function is going to increase very quickly as we move to the left. It's actually decreasing as we move to the right. And it's going to get closer and closer to that horizontal asymptote, but with ever crossing or touching it. So this is a pretty good approximation of what that graph would look like. I may have missed some exact points here toward the top, but overall this is a pretty good approximation. So the domain here includes all real numbers, no restrictions on x, and the range now is going to go from -4 to positive infinity with -4 not included. Next, let's look at the principle of exponential equality. For any real number b, where b is not equal to -1, nor 0, nor +1, b to the x power being equal to b to the y power is equivalent to the statement that x must be equal y. In other words, if two powers that have the same base are equal, then their exponents must be equal. Let's use this to solve some of the following equations. In fact, here we're asked to solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u power is equal to b to the v power. So we have 5 to the x is equal to 125. I'm going to write this as 5 to the x power is equal to 5 to the third power, because 5 times 5 times 5 is 125. So we see here we have two powers that are equal and they have the same base, so the exponents must be equal. This one was pretty simple. In the next example, we have 2 to the 3x minus 7 power is equal to 32. Well, the left-hand side is already written as a power of 2, but I'm going to rewrite 32 as 2 to the 5th power, because 2 to the 5th power indeed does equal 32. So I have two powers that are equal, and they have equal bases, so their exponents must also be equal. This gives me a linear equation that's quite simple to solve. I first add 7 to both sides to get 3x is equal to 12, and then I divide both sides by 3 to get that x must equal 4. In the next example, I have 3 to the x minus 9 power is equal to 1 over 81. I'm going to write 1 over 81 as a power of 3. So we have 3 to the x minus 9 power is equal to, well, 3 times 3 times 3 times 3, or in other words, 3 to the 4th power is 81. So 1 over 81 would be 3 to the negative 4 power. Now that I have two powers that are equal with bases that are equal, I can set the exponents to be equal to each other, which gives me that x must equal 5. Next, I have the cubic root of 5, all raised to the x power is equal to 25. On the left, I'm going to write this as 5 to the x over 3 power, and 25 I will rewrite as 5 squared. Two powers that are equal, that have equal bases, will have exponents that are equal. So x over 3 must equal 2, and then multiplying both sides by 3 will give us that x must equal 6. Next, we have 3 to the x squared divided by 27 to the x power is equal to 81. I see a square, so I'm predicting that this one might be a little bit more work. Let's see how we can rewrite these as powers of 3. I think 3 is the common base that we're going to aim for. So I already have 3 to the x squared power. I'm going to write 27 as 3 to the 3rd power, which it is. And then 81, as we saw earlier, is 3 to the 4th power. Now on the left-hand side, I'm going to rewrite this as 3 to the x squared minus 3x power. I'm going to use a couple of rules all in one step. First of all, in that denominator, we have a power of a power. So that's going to become 3 to the power 3 times x. And then finally, as I look at the entire left-hand side, I'm going to use the quotient rule for exponents, where we subtract exponents. So now I have two powers that are equal with equal bases, so it must be that the exponents are equal. So x squared minus 3x must equal 4. And that gives me a quadratic equation. So I'm going to clear the right-hand side and write this as x squared minus 3x minus 4 equals 0. And using factoring, I'm going to write this as x minus 4 times x plus 1 must equal 0. So either x minus 4 is 0 or x plus 1 is 0. So either x is 4 or x is negative 1. That means that we have two solutions to this equation. Now, let's be careful here. There was a square involved, and I want to make sure that we don't have any extraneous solutions. In other words, values that appear to be solutions mechanically, but that don't actually work. So let's see, for instance, if x minus 1 works. That's the one that I'm a little bit suspicious about. So if x is negative 1, we have 3 to the negative 1 squared power over 27 to the negative 1 power, and that's supposed to equal 81. Well, in the numerator, negative 1 when squared just becomes a positive 1, so we in fact just get 3. And in the denominator, 27 to the negative 1 power actually is going to become 27 to the positive 1 power when moved up to the numerator. So indeed, I think this works. 3 times 27 does equal 81, so that is a true solution. And I forgot my negative sign up here, but I think I did the substitutions correct when x is negative 1. Let me write that a little bit more clearly so that as you look back at the notes, it makes sense. So I did do the correct substitution, I just didn't write that as correctly. Secondly, when x equals 4, let's just make sure that we are convinced that is a true solution. When x is 4, we have 3 to the 4 squared power over 27 to the 4th power, and that is supposed to equal 81. So let's see, 3 to the 16th power over 27 is 3 cubed, and that's going to be raised to the 4th power. It's looking good because this is 3 to the 16 over 3 to the 12, and that's going to become 3 to the 4th, which indeed does equal 81. So we are good with both of these solutions, but I think it was worth it to kind of go through the check to see why this works. For the next example, we have e to the 2x plus 1 power is equal to the 4th root of e. So we can write this as e to the 2x plus 1 power equals e to the 1/4 power. And we have equal powers with equal bases, and so the exponents must also be equal. If we subtract 1 from both sides, we get that 2 is equal to 1/4 minus 1, but I'm going to write the 1 as 4/4 so that we can actually combine those two terms. So we get 2x is equal to negative 3/4, and if we divide both sides by 2 or multiply both sides by 1/2, we get that x must equal negative 3/8. All right, for the example 7, we have e to the x squared power all squared is equal to e to the 8th power. So the left-hand side we're going to write as e to the 2x squared power because we have a power of a power, and so the exponents have to be multiplied. And that's going to equal e to the 8th power. So we have equal powers with equal bases, so the exponents must be equal. Dividing both sides by 2 gives us that x squared is equal to 4. And next, using the square root property, we see that x must equal plus or minus the square root of 4, which is plus or minus 2. So we have two solutions here. Either x is positive 2 or x is negative 2. In example 8, let's rewrite that right-hand side as e to the negative x plus 30 power. And we haven't seen this rule so far in these notes, but it's a previous rule that says a to the m times a to the n equals a to the m plus n power. So when we multiply e to the negative x by e to the 30, we're actually going to be adding those exponents. We have two powers that are equal with bases that are equal, so now we're going to set the exponents to be equal. And it looks like this is going to give us a quadratic equation, so let's go ahead and clear one side. I'll write this as x squared plus x minus 30 on the left and 0 on the right. This is factorable, so let's write this as x plus 6 times x minus 5 equals 0. So either x plus 6 is 0 or x minus 5 is 0. So we'll get that x is equal to negative 6 or that x is equal to positive 5. So we'll have two solutions here as well.